Good morning, dear students. I am Dr. Nirmalo Chandra, Associate Professor of Murshidabad College of Engineering and Technology, a government-aided institution supported by Murshidabad Jilla Parishad. Today, I am discussed about a topic under digital communication system. The name of the topic is quantization technique in digital communication system. Now, in digital modulation technique, signals are basically represented by a list of binary number like 0, 1, like this. So, if the digital transmission techniques are to be used for any analog signal, the sample signal is required to be quantized. So, quantized means a set of countable levels. The signals, like any type of signals, this type, like this. So, these signals is in discrete in time domain is reformed as like this. So, it will be named as 0t, 2t, 3t, 4t in this way. So, this signal is discrete in time, that is known as sampling signal. Sorry. So, this signal, the above signal is discrete in time, that is known as sampling, as well as the above signal is discrete in amplitude, that is known as quantization. So, this signal discrete in amplitudes as well as discrete in time, both will referred as quantized signal. Now, in the case of discretization in amplitude, that is in magnitude level, the sample countable value is just rounded up to the nearest quantization level. The sample countable value, sample countable value is rounded up to the nearest quantized level. For that, as the signal here is rounded up, so the error is created. This error is actually known as quantization error. This quantization error is equivalent to noise that adds or subtracts from the actual samples, known as quantization noise. So, quantization noise actually difference between the sample value and the rounded up value. The sample value difference between sample value and the corresponding rounded up value. Now, if x of t is x of t represent the actual signal and the signal passes through the quantizer, then the output of the quantizer is denoted as x of q nts, that is the output of the quantizer. Then the difference between then the x of q of nts is the discrete form of that actual signal. And the difference between this is x of nts, one second, this is not x of q nts, this is x of nts. X of nts is the discrete form of that actual signal. Then the difference between x of nts and x of q nts known as quantization error. Now, classification of the quantization. Classification of quantization. quantization is two types. First is uniform quantization. Another one is non-uniform quantization. Again, uniform quantization is two types: mid-rise and mid-trade. Now, for uniform quantization, I draw the two types of figure, that is mid-rise and mid-trade. This is in y-axis, this is output level, and in x-axis, that is in horizontal axis, this is input level. And the quantization pattern is like this. Here all step size, as it is handmade drawing, but remember the all step size, all size of the staircase pattern are equal. And here you see the input output characteristic staircase pattern goes middle of the rising part of the equation, rising part of the origin. That is why it is named mid-rise. This is mid-rise. Here the staircase pattern is increasing at the origin in rising part at the vertical lines. So it is mid-rise. Similar way, for mid-trade, I will draw the pattern. The figure is like this. This is as usual the two axis. This is input level, the horizontal axis, and in the vertical axis this is output level. Here the staircase pattern is like this. So here the input output characteristic staircase pattern goes middle of the trade at the origin. So it goes to horizontally move at the origin. So this is known as mid trade. So these are the two types of uniform quantization, mid trade and mid rise. Now as we know, the quantization noise or quantization error in previous I already discussed, that is the denoted by epsilon. Epsilon equals to quantization error. So this is equal to just x of q nts, that is the some quantized value of the analog signal and the corresponding sample value, that is the discrete value of the analog signal. This is quantization error, also denoted by Q of NTS. So in the below figure I will draw the two type of pattern. Just look at it. Here I will draw the staircase pattern of the quantization is mid-thread type, that is it goes at the origin horizontally. You can also draw it and mid-rise type. This is the quantized pattern of the signal. Here we take as a reference RAM signal. So this is the quantization, that is the staircase pattern of the RAM signal, and corresponding discrete value of the discrete pattern of the RAM signal is like this. So it is like this. This is a straight line, RAM. So here it is RAM signal in discrete, RAM signal in discrete pattern, and this is the corresponding quantized staircase pattern of the RAM signal or RAM voltage, whatever you can say it. So here you see this is X of QNTS and this yellow figure is X of NTS. Now in the above figure we point out the 2 points. This is A and B, like this point is, say it is A, and okay, there is a one mistake, small mistake. I redraw the staircase pattern again. This is like this, then it is correct. Now the above point we pointed out the 2 points, it is A and in the below it is B. Then just see the yellow straight line is in between, goes in between A and B, goes through in between A and B. So here what is del? Del is the difference between the point A and B. Difference between the point A and B denoted by, difference between the point A and B is denoted by del. So this del is actually known as step size. And the quantization noise, that is the epsilon, is lies in between minus del by 2 less than equal to epsilon less than equal to plus del by 2. Why? Because you see, if you see minutely, you can see it that yellow straight line goes through on the A and B point. So if somehow if the original signal is below of A point, then you have to subtract the point to get the main point, and if the original signal is above the B point, then you have add some portion. So actual point lies in between A and B. What is the actual signal value lies in between A and B. So we can assume that the quantization error, which is difference between the quantized value and the main sample value, is always lie between minus del by 2 to plus del by 2. So if we think about uniform quantization, if we think the probability density of the uniform quantization is uniformly distributed, then the corresponding figure is denoted by the like this. This is the figure of probability density function of uniform quantization. This is plus del by 2 point, this is minus del by 2 point, this is the 0. Then just draw the distribution function is like this. Then like this. So this is the, as it is uniformly distributed, so the point is also uniform. It is A, it is 2A, and this is the PDF, that is probability density function. It is the PDF. It distributed like this. Distributed as uniform distribution function. So in the previous figure, that is this figure, here you see at point A, that is this point, the sample signal, that is quantized signal x of QNTS, this is x of QNTS, is above the sample signal, that is x of NTS. So here it is above the x of NTS signal, and at point B you see that this x of QNTS is below the main sample signal, that is x of NTS. So that is why we decided that epsilon, that is the quantization error, which is the difference between these two, x of NTS and x of QNTS, is lies between minus del by 2 to plus del by 2. And what is del? del is just nothing but difference between A point and B point, the mod value of this A point and B point. And the next figure is the uniform distribution function, which have the probability density function of this uniform quantization. So this is the distribution. How you can distribute it is like this. So if we maintain the uniform quantization of this figure, we draw the probability density, how it can distribute it. Just see the figure, I will draw it. So this is the figure of probability density function, that is lies between minus del by 2 to plus del by 2, and the value of the probability density function, that is denoted by P of epsilon, probability density function of the quantization error, that is uniform quantization, that value is denoted by 1 by del in the vertical axis, this point. Here we can draw the figure with respect to this uniform quantization noise, and this is the probability density function. Now here, if we evaluate the variance of this uniform distribution function, we can get the value like this. The variance is denoted by sigma epsilon square, that is equal to integration minus infinity to plus infinity. It is a general expression, that is P of epsilon, that is probability of this, into epsilon square dq. Now here we see that the limit is bounded up in between minus del by 2 to plus del by 2. So that is why we can rewrite the expression is like this, that is integration minus del by 2 to plus del by 2, and obviously what is the value of this probability P of epsilon? It is from figure you can see it is 1 by del, then epsilon square d of q, or sorry, it is better you can write it is not d of q, as we represent the epsilon error in epsilon, so it is d of epsilon. Similar here also it is d of epsilon. Now just evaluate the integration, you can see it is 1 by 3 del epsilon cube plus del by 2 to minus del by 2. So this is equal to ultimately del. Okay, in next page I will express this because space is not sufficient here. In the next page, this is equal to del by cube by 8 minus of minus del cube by 8 by, this is 8 by 3 del. So this is equal to 2 del cube by 24 del. So ultimately it is del square by 12. So this is very important formula, that variance of uniform distribution function like the above figure is equal to del square by 12. This is the actual quantization noise power. This is also known as quantization noise power in case of uniform distribution function. And now if we think that in this way, that we can take a signal, assume we can take an analog signal which is denoted by x of t. Then we can draw the following figure. So the upper value of this analog signal is VH, the lower value is VL, and the quantization levels of this analog signal we can labeled as like this. It is first S0, then S1, then up to in this way is m minus 1. So we can divide it the total level of the analog signal in m number of levels we can set it. This m number of level actually signifies the quantization level, and correspondingly if we goes through the step size value, that is staircase pattern value, then it is denoted by del, which is denoted by del. Then the level of the sample is like this. First of all is VH is the highest value, then next value means in the below portion, next value is VH minus del, then VH minus 2 del, like this. Similarly in the lower case, low value is VL, then the above value of VL is VL plus del, VL plus 2 del, like this. So we can label here in this way. First of all it is VH, okay, change the color so you can easily understand. It is VH, next is VH plus del, next one is VH plus 2 del, in this way. Similarly in the below portion it is VL, next is VL minus del, VL minus 2 del, like this. So this is the two difference. Just you see VH plus del, VH plus 2 del is sampled, and S0, S1 up to S minus 1 is quantized. So difference between two gives you the error. Now from the probability density function, when we evaluate the probability density function, then we here we see the corresponding figure, which is like this type of figure we see, which is the figure of probability density function versus the quantization error, probability density function of the error, and this is the quantization error if silent. And correspondingly we also draw the analog signal, which is this, and its corresponding quantization level, and we can divide it. The total number of levels is up to m, and highest limit is VH, highest value is VH, lower value is VL of the main analog signal, and quantization level is denoted by S0 up to S minus m minus 1, in this way. So here VH minus VL is equal to m into del, where m is the number of levels and VH minus VL is the total difference. So this equation is easily comes out. What is del? Del is just difference between the two levels. Difference between the two levels, del, equal to here each and every step size. Each and every step size of the level is del. So basically from that equation, del is equal to just because VH minus VL divided by m. Total number of levels is m. What is the unique levels? Unique levels is del. So del is equal to VH minus VL by m. Now as how we can evaluate this density function distribution. As we know, the quantization error has zero mean uniform probability density function over the range minus del by 2 to plus del by 2. That is why the equation comes, that is sigma epsilon square is equal to, ultimately epsilon square cap is equal to zero mean uniform probability density function, and that is actually denoted by one second, that is equal to integration minus del by 2 to plus del by 2 p of epsilon into epsilon square dq, and we see that the value, ultimately the value is del square by 12. So this is very important. Now what is the SNR? What is the corresponding SNR? SNR means signal power by quantization noise power. Quantization noise power, signal power by quantization noise power, that is equal to PS, that is the signal power, assume average signal power PS divided by quantization noise power, which is epsilon square cap. This is equal to ultimate PS by del square by 12 as we evaluate in previous equation. So it is ultimately equal to 12 PS by del square, and the unit is expressed here in dB unit, that is decibel. So ultimately this is equal to 10 log base 10 SNR, that is signal to noise ratio, signal power by quantization noise power ratio, that is basically equal to 10 log base 10 12 PS by del square. So this is the SNR of uniform quantization. So all these things is for uniform quantization. I think you all understand this. Now we discussed about non-uniform quantization. Non-uniform quantization. So non-uniform quantization, what is this? Where quantizer characteristic, where quantizer is non-linear, characteristic of the quantizer is non-linear, and step size is not constant, instead if it is variable, step size is not constant, instead if it is variable, depend on the, if it is variable, depends on the amplitude of the input, then input signal, if it is depend on the amplitude of the input signal, then the corresponding quantization is known as non-uniform quantization. So this is the valuable two points where the step size is not constant and quantizer is non-linear. Then the amplitude of the input signal is then the amplitude of quantization is known as non-uniform quantization. So as the step size is not uniform, so where it is basically used? This is particularly helpful when the signal amplitude remains very small over an authentic time period. Okay, where the signal amplitude remains very small in authentic time period, just like your musical signal. That means in sound system you can see it practically. So as the step size here is non-uniform, then so it is varied accordingly to the signal level to keep the signal to noise ratio in adequately high. Okay, so as here the step size in case of non-uniform quantization is non-uniform, so signal to noise ratio adequately high to keep the signal level in permanently cleanly. Now let's think about the probability density function of the signal, that is non-uniform signal or basically non-linear signal. So here we draw the non-uniform step size of probability density function Fs of that input signal. So Fs is the probability considered, here we consider Fs is the probability density function of non-uniform step size, then what is its corresponding figure? We will draw it. This is Fs, probability density function of non-uniform distribution function with respect of S. So here we select the 2 point AI and BI. Difference between AI and BI is HI. In between there we will choose this value which is known as SI. It is 0. So the lower value of the fs is s minus s max and higher value of the sx is positive plus x max. Okay, si is the levels plus minus s1 plus minus s2 are these levels are closely spaced near the center where when fx is maximum, that means see this si is closely spaced when fs is maximum, that is this point. In this point s1 s2 are closely spaced. Okay, reverse case, when fs is decreasing, that is in this region, that is in this region or this region where fs decreasing, here also fs decreasing. So in this region si, that is the the levels becomes large. Here the si, that is the quantization levels are large. So s minus si, so from the above figure s minus si denotes the quantization error, that is epsilon I. Now here from the above figure, that is from this figure, hi equal to bi minus ai and si equal to ai, as it is in between the 2 points is ai and bi, so it is ai plus bi divided by 2. From this 2 equation we see that from there 2si equal to ai plus bi, that means bi equal to 2si minus ai. So here we put the point hi, ultimately hi equal to, as bi equal to this, so if we put the value bi equal to 2si minus ai then minus ai, so that is ultimately equal to as we see here b 2si minus bi equal to bi. Okay, here similarly, okay, nothing else. So here hi equal to 2si plus 2ai, isn't it? So hi by 2 ultimately equal to si plus ai, sorry, one mistake, it is minus 2i, so here it is also si minus ai, this is minus ai 2ai, so it is si minus ai equal to hi by 2. So ultimately AI equal to Si minus Hi by 2. So ultimately Hi equal to Ai plus Hi equal to Ai minus Bi, Ai equal to Si minus Hi by 2. Similar way, Bi equal to Si plus Hi by 2. Now if we calculate the probability density function of that non-uniform quantization, that is the figure this, that is the figure this, that is non-uniform figure, and the 2 point is that is the figure is this, it is plus S max to minus S max, and this is the 2 point. Difference is Hi, it is Ai Bi, in between it is Si, in between it is Si. So if we evaluate the probability density function value of this non-uniform distribution, that is denoted by epsilon square. This is actually quantization noise power. This is equal to likewise the previous uniform quantization formula. Similar way, integration upper lower limit Ai to Bi, S minus Si, that is the quantization noise power into Fs ds. It is the variance, it is likewise the variance of the non-uniform quantization PDF, probability density function. Okay, so this is the equation S minus SS square. Now concentrate the figure again of non-uniform quantization. This is the figure. This is minus plus S max quantization level, this is minus X max, this is Fs, this is lower limit Ai, this is the higher limit Bi. In between the quantization level we assume it is Si. Now here when Fs is decreasing, from this figure, mod of Si becomes large, and when Fs is maximum, that is the peak point, when Fs is maximum, then mod of Si becomes small. So this is the two valuable 2 points. So in the above equation, S minus Si, above equation, that means this equation, S minus Si equal to quantization error s minus si is equal to renamed as quantization error, which is epsilon I, and this epsilon I square equal to mean square quantization error. Now next is calculation of epsilon I square cap in discrete domain. Here epsilon I square equal to in summation form 2 into summation epsilon I square I is equal to 1 to m by 2, that is summing epsilon I square over m by 2 intervals. So this is this. So for 2, why we calculate this 2? Because 0 to m by 2 is m by 2, and m by 2 to m minus 1 it is another m by 2. So ultimately if we put 2m by 2 we will get m. Okay, that is why this 2 coming. Now from the above equation we put the value epsilon I square, that is equal to 2 into summation I is equal to 1 to m by 2 integration ai to bi s minus si square fs ds. So this is equal to 2 into summation f of si, where I is equal to 1 to m by 2 integration, put the value lower limit and higher limit, si ai equal to si minus hi by 2, as we see from above equation. From this put the value ai and bi, then we will get si minus hi by 2 to si plus hi by 2 s minus si square ds. So this is equal to ultimately 2 into summation f of si I is equal to 1 to m by 2, and if we evaluate the integration we will get it is equal to 1 by 12 hi cube. Just put the solve this part, just solve this part, you will get this. Now this is equal to, now for non-uniform quantization, we assume f of si equal to 1 by 2 del. For uniform quantization, for probability density function, it is 1 by del PE, and here it is 1 by 2 del. And you know, HI is equal to where it is del, just reference the AI and minus BI, which is step size. Now, to find the best location, of the quantization level of an analog signal, find the best of quantization level of an analog signal, the expectation, that is the EX expectation of the quantization noise EI should be zero. So integration AI minus BI S minus SI, that is the expectation of EI, is equal to S minus SI Fs ds equal to 0 for all I. Following this equation, actually following the above condition, the signal is first compressed in a non-linear device and then uniformly quantized. The distortion of this compressing is undone at the reconstruction by an expander having complementary, this is the important point, complementary complementary nonlinearity. The above two processes are known as compending. So compending basically equal to compression plus expanding. The corresponding block diagram of the compending is like this. It is the compending model. I will draw the block diagram. That is, first of all, one analog signal is come, analog signal as the input, which is of t, suppose it is ST, it is comes through a level which is known as this is the first block, this is the second block, then third block, after that fourth block, then fifth block, ultimately main analog input after sixth block. So what is the name of each and every block? I will write here. First block, it is compression. Suppose it is denoted by YS. Next is sample and hold circuit. Then from there you will get the PAM signal, pulse amplitude modulation. Then this pulse amplitude modulation signal is passing through a E to D converter. Here the analog signal is converted into digital and which is known as PCM, pulse coded modulation signal. Then it is again transferred into analog signal by D to A converter. Then it is again formed as PAM, that is pulse amplitude modulation. Then it is again goes through a whole circuit. Then after that is passed through a expansion, that is expanding. It is complementary of compressor, it is Y inverse S. Then you will get the analog output. The total process known as, total process is the block diagram of total process, sorry, is the block diagram of compounding. Now from the above block diagram of compounding, we will draw the following figure of the compressed output, which is Y of S. So this is the compressed output of Fs and it is corresponding analog signal in the Y axis. It is output, in the X axis output, and in the X axis it is input of S, and in between we will find out the 2 points, which is A and B. As usual, it is difference is HI, upper limit is BI, lower limit is AI, is 0, and the difference between A and B is del. You know from this, it is from previous figure. So here if we compare this figure with this, so here you also see this A and BI. Then how can you solve the compressed output, which is YS? How can you solve this compressed output YS? You just follow the following techniques. So at first we have to differentiate the YS, that means the slope. What is the slope of this YS, which is red colored waveform? It is denoted by Y dash S, that is equal to dy by ds at about s is equal to si. So this is equal to the del slope means if how can we evaluate just converted the nonlinear into linear form, that is we will draw here a tangent part, we will draw here a tangent part, then you will get it. What is this? It is del by hi, that means this part, this is hi, the difference is del, so this is del, this is hi. So del by hi gives you the corresponding slope of this red color signal. So this is the slope, how you can evaluate. Now the output is uniform quantized, the result is non-uniform quantization of ST with increasing steps for higher signal levels. So if the above figure, if the output is uniform quantized, the result is non-uniform quantization of ST with increasing steps for higher signal levels. So this is the important point. So if the output is not uniform quantized, then the result is non-uniform quantization of ST with increasing steps for higher signal levels. The slope of the curve now is denoted by y dash L equal to slope of the curve, and this is equal to dy by ds. Why we can follow? Just for evaluate the compressed characteristic. So if del, that is the step size is small over AB, that means from this figure this is the A and B point. So from the point AB, the slope here straight line, that is the tangent of the curve A to B, that is the tangent of the curve A to B. Now from equation 3 we see that y dash is ultimately equal to del by hi. This is the equation named as 3. So this from this equation hi square equal to actually del by y by dash square. So if we put this hi square in previous equation, where we can see epsilon square equal to just 1 by 6 summation I is equal to 1 to m by 2 I to m by 2 f of si into del square divided by y dash s square into hi, and now if we put this value here, we have epsilon square equal to ultimate del square by 6 integration 0 to 1 f of si divided by y dash s square ds. So ultimately, what is the SNR of the non-uniform quantization? It is x square by s square by epsilon square, that is equal to fs by del square by 12 total divided by that is equal to total divided by 2 into integration the above part 0 to 1 f of s divided by y dash s ds. So this is equation number 4. So for digital communication, in PCM system, the factor 2 into 0 to 1 f of s divided by this y dash s ds accounts for actually compression. So this is the main compressor value of the compounding signal. Now how you can evaluate this? For that we can choose the two law. First of law is A law, another one mu law. Mu law and A law, this is known as compounding. A law compounding and mu law compounding. Mu law compounding is denoted by this equation y of s equal to actually plus minus log base e 1 plus mu s by s max divided by log of base e 1 plus mu. This law is used in USA, Canada, etc. and Japan. The standard curve of mu law, I will draw it. This is the characteristic curve of mu law. This is the variable value of mu. The linear value of mu is 0, then mu is equal to 1, then mu is equal to say 100, and standard value of mu is 255. Mu is equal to standard value of mu is 255. This is the ys by y max in vertical level. In horizontal level it is xt by x max. This is the characteristic of mu law. And next one is A law. For A law compounding, I will draw the characteristic curve. This is the variable characteristic of A. This is A is equal to 1 for linear, then A is equal to 2, then ultimate A is equal to 100. The higher value is 1.0, with respect of it is also 1.0. S by S max horizontal level, Y S by Y max vertical level, and ultimate equation ys by y max equal to plus minus a into s by s max divided by 1 plus log base a for 0 less than is equal to s by s max less than is equal to 1 by a, and another value is for a log equal to plus minus 1 plus log a s by s max by 1 plus log a for 1 by a less than equal to s by s max less than equal to 1. Now standard value of a is 100 and it is used in Europe. Now what is the difference between these two curves? A law, it is the mu law curve and it is the A law curve. What is the difference? Difference is that the most important difference between the two type of compression is that A law compressor has a mid riser at the origin. That is why the value of A is non-zero value at the origin level, whereas mu law, it is at the origin it follows mid rate. This is the main difference between mu law and A law. So this is up to the non-uniform quantization technique in digital communication system. Thank you.